Postgres started as an object relational database with its own query language. Well, not SQL. But today, with the right extensions, it can behave like a document store, a columnar database, even a time series engine, without ever leaving the SQL ecosystem. In this video, we'll explore the power and limitations of Postgres extensions. Let's build up your data skills. From ETL and analytics with Spark and DuckDB to querying JSON and XML or handling everyday transactions, SQL is everywhere. Data engineers, data scientists, analysts, and stakeholders across the business all understand SQL. It has become the great unifier, and it is now more important than it has ever been. I was curious about the state of Postgres and whether or not I could truly become a Postgres maximalist, so I started thinking about all my storage and querying needs, and I split them into categories. Then I searched for extensions that would best fit my requirements and selected a few to test out. In this video, I'll give you a rundown on Postgres extensions for pretty much every use case you can come up with. You'll be able to follow along through the following GitHub Repo, where you'll find a custom Docker image running Postgres 16 and all extensions I'll be covering here, along with a few other services I bundled into a Docker Compose just for you. Among other things, we'll build a very simple time series anomaly detection system on top of a YouTube trending videos dataset from Hugging Face, and we'll also build up a text-based recommender system that neatly summarizes the movies it picked out for you based on a fairly recent dataset. Exciting enough? Let's dive in. So in order for us to become a PostgreSQL maximalist, we need to identify which use cases are required for our storage and querying needs. So let's begin there. Perhaps the most trivial one is documents. We need to store, query, but also validate documents in relates to their schema. This might go for key value pairs, which is a really generic way of storing documents, JSON, which is perhaps the most conventional one, and XML. All of these are built into Postgres, but we'll get there. Another big one is analytics and time series, where efficiency is key. This is where columnar formats come in, which enable aggregation queries to be ran efficiently. There is table partitioning, which splits your table into multiple subtables, which essentially limits the maximum size of your unitary table. There is incremental materialized views, which means that the materialized view is updated only on changed data. Again, this is useful for time series. Flexibility is also important. Can we integrate it with external table formats or not? Can we use object storage, which is cheaper, and particularly for analytics where you might be supporting some kind of lakehouse architecture? Object storage is key. Reading from multiple data sources and formats. We all know that DuckDB is getting some traction there, so that's an essential one as well, because it will support your ETL tasks as well as your analytics tasks. Data versioning, this is something that comes for free with table formats, but it's not something that is very common on Postgres yet. Compression and retention policies. This is particularly useful for time series, especially the retention policies where you'll limit the amount of data you are keeping based on date or number of records if for some other context. Then we have vectors and AI, which is kind of a hot topic, and it is discussable on whether or not AI should be done directly on the database or whether it's required. But for that we need a vector data type, which usually comes with PG vector, and it's been around for a while now. We need distance metrics, so we can compute the distance between vectors. We usually rely on approximate indexing because, you know, computing, let's say that we have 1 million vectors and we want to compute the distance between all those vectors, or at least, you know, compute the distance between one of those vectors and every other vector. This will take a while, so having some kind of strategy for approximate indexing will give you the k-nearest neighbors much faster than it would if you did the operations from scratch, you know, without any support data structure. Then these usually provide text embedding and semantic search for text embedding, and this is where it starts to, at least I start questioning whether or not it's the best approach to do this in the database, because usually when you are, you know, buying an instance, paying for an instance where you have your database running, whether it's just a VM or a managed instance or whatever, you are focused on usually on storage above all, and then perhaps CPU and memory, or perhaps memory first, right? But you don't really have a GPU there. So in order for us to do AI directly in the database, we probably need an instance with a GPU, unless of course we are connecting through APIs to ChatGPT or something like that, which is also viable, you know, but more expensive. And finally, usually the end goal of these AI extensions is to support RAG, so retrieval augmented generation. Some of them provide general LLM querying, some don't, you know. But this is more or less the requirements we should set for AI on a Postgres database. And again, like I said, it's discussable whether or not this is the best place to do it, but let's look into it. Then we have search, and by search I really mean full text search, where we need an inverted index structure. There is one called GIN, a general inverted index on Postgres already, but there are other extensions that do this a bit better. We usually need a text pre-processing pipeline. Again, Postgres has a lot of stuff already built in to help you with this, but there are extensions that make it easier to configure all of this. You need ranking functions, and Postgres just provides two example functions. Really, they work, but they are not the best you can use for ranking. And then it should support a set of basic operations like Boolean operators and or negation, field-based querying, term boosting, dog is more important than cat, for instance, phrase queries, so you have two words that make up a single term, fuzzy matching, which means you just misspelled a word by single letter and it can still match it with the documents containing that word, or maybe the document has been misspelled and you can still match with that document. And stuff like range filtering can be useful as well, for numbers, but for dates as well, For graphs, this is perhaps where Postgres lacks the most, because one property for storing and querying graphs is that we need index-free adjacency. So essentially, the way the graph is stored is like an index itself. This means that for every node, you know the exact offset in disk where its neighbors are. We need graph metrics, so stuff like measuring the diameter of a graph or the average path length of a graph, or the coefficient, the clustering coefficient. Node centralities are also a must. Stuff like page rank or betweenness centrality or closeness centrality. Clustering algorithms, which can be community detection algorithms, or you know, the k-click or something like that. Path finding algorithms, which usually means you know, the Dijkstra or A* for computing shortest paths, but it can also be functions for producing random walks in a graph, which can be useful, especially if you are sampling the graph or trying to compute some kind of approximation to another algorithm. And finally, node embeddings, which is really a must nowadays. This means that you are essentially converting a node into a vector, a numerical vector, where nodes with a similar neighborhood have a high similarity when you measure, or low distance when you measure the distance between them. Then finally, this is kind of a bonus one, let's say message queues. We can implement message queues or think about message queues in two ways. One is the producer-consumer pattern, one-to-one, which is most common for, you know, job queues or something like that, and the publisher-subscriber pattern, one-to-many, where you usually have some kind of a broker and different software, different clients subscribe to a topic and get, you know, when the topic is published, an event is produced, and subscribers are notified and they can read the message. For operations on message queues, we usually just need three basic operations. We need to be able to create queues, different queues, send or publish messages to a queue, or receive and subscribe to messages from a queue. Another interesting one is visibility control, because you might want to read a message from a queue and make it invisible to other workers while you are trying to process that message. Sometimes you can extend visibility as well. If you are, let's say, you predict that you are going to work on a task for 5 minutes, it's taking more than 5 minutes, and you add 5 more minutes to make the message invisible, to keep it invisible. You can also do delayed sending, which really works as a form of scheduling, for instance. So before getting into the Postgres extensions that we researched, let's do a quick run of the Docker image that you can use to, if you'd like to follow along with the video. So if you go into Data Lab Tech TV at GitHub, you'll find a PostgreSQL Maximalism repo, which should be public by the time this video is released. In here you'll find Docker Compose that includes a PostgreSQL 16 installed with several extensions that we'll be using throughout this series. You are recommended to run at least Docker 2010, which has Docker Compose included. You can optionally run NVIDIA Container Toolkit if you'd like to run the AI stuff on your machine. If you have a graphics card that can support the model, then you should install this as well. There will be a .env.example file that you can copy to a .env and replace with your own credentials and database. There is also a configuration for min.io and a bucket, which will be used by PG Mooncake. You are also recommended to since we will be building from source all the extensions, you are recommended to create a builder with a maximum parallelism of 1, just because each extension is already parallelized during compilation, and Docker Compose will attempt to compile several extensions at the same time, and that will likely just freeze your machine. So this is optional, but not really. Then you should wait for the Minio, MC and Ollama models to exit, because these are initialization containers. Let's just go into Docker Desktop. So our PostgreSQL Maximalism stack consists of a Postgres 16 running all the required extensions, an Ollama and PGAI worker service. These will be used during our AI extension demo. Then we have MinAO, which is used during our analytics extension demo, and WhoDB, which is a SQL client, a web SQL client that has some AI integration, and we'll be looking at that just out of curiosity. Now if we go back into the repo, you can connect. After this is running, you can connect easily by exporting the variables on your .env, because they are standard Postgres environment variables. You can just call PSQL without any arguments and you will be connected to the database. Then you can list all the installed extensions, all the active extensions, using /dx or using this equivalent query. That's it. Let's get into it. In this video we used the Harlequin SQL IDE for the terminal. This is a really cool project that I believe it's quite recent, and it ships with a DuckDB adapter, but it has adapters for a ton of other databases, and it works with mouse if you like to use mouse, so it's really not an issue there. You can use it like a regular GUI, but for the Postgres adapter it had some issues, particularly with returning JSON with fields that do not exist, and also it wasn't able to handle $$ for string quoting, which is something that is quite basic when you're writing Postgres for creating functions and stuff like that. So it still needs some work, but it's a really nice project. It's in between just a simple REPL for Postgres and something more like a UI. It's still lightweight enough that you can use very easily via terminal. We also used pgcli, and pgcli provides a REPL for Postgres, kind of like PSQL, but it has completion and it has syntax highlighting, which is quite nice. So I like this one a lot as well. Doesn't have any issues with $$ or listing fields from a JSON fields that do not exist. Finally, we also use SQL tools inside VS Code. We just didn't use it for the video because to zoom in, and it just there just wasn't enough space to show the output window at the same time we were showing the code, so it didn't make sense to use the same client. So as you can see, this one also has a ton of support for multiple databases. I see support for AWS Redshift, but not for RDS, curiously, but you can always tunnel into your local host and then connect through there. Although they do have one for cloud, Google Cloud SQL. I don't know why, but yeah. Next time, we'll cover document storage and how to use open table formats to support your analytics tasks on Postgres. You can find the unedited research notes for this series as a blog post at datalabtech.tv, and you can also take a peek at the upcoming content for the following parts. Don't forget to drop a like and subscribe for all things data.